In this video, we'll talk about how to deal with collinearity and regression, and we'll also talk about dealing with categorical variables that depend on other categorical variables. So when we deal with correlation, it goes from a strong negative correlation to a strong positive correlation. So if you have -1 to +1 as your range, the closer you get to the extremes, the stronger the correlation. And it doesn't matter whether you have a negative correlation or a positive correlation. So for example, which correlation is stronger, -0.8 or +0.8? They're both just as strong. It just means for the negative correlation that there's a linear relationship, so as one variable goes down, the other goes up. And with a positive correlation, as one variable goes up, the other one also goes up. So let's talk about collinearity and multi-collinearity, and how do we measure it and what can be done about it and why does it matter? Collinearity is when once there's a strong bivariate correlation relationship between two input variables. And multi-collinearity is when you've got multiple input variables beyond two that have a strong relationship together. So here's an example. So here's a correlation matrix where we have the y values, the correlations of the input variables with the dependent variable. And so you can see that there's a reasonable relationship between the input variables and the outcome variable, but there's this very strong correlation between two of the input variables. In this case, input variable 2 and input variable 3 are strongly related. So what does this mean? Well, this means that there's a lot of shared information in these two variables. In other words, they're not independent. They depend on one another, and there's a lot of shared information. It also happens when that's a negative. So in this case, we've got a very strong negative correlation. So there again, there's a lot of shared information in these two variables. This is an example of multi-collinearity. In this case, we have a strong relationship between IV2 and IV3, but we also have a strong relationship between IV1 and IV3. So in this case, we have two strong relationships, or we have three variables that are strongly related, and we need to make some decisions about what to do. Now, if we leave everything in, there can cause some problems for when we're estimating the coefficients for our regressions. Because what ends up happening is it tends to distort the value of the correlation, or excuse me, it tends to distort the value of the regression coefficients. So you can get them so that they're artificially suppressed. You can get them so they bounce around. So depending on how you sample and pull data, that they change quite a bit, and that's not a good thing. And you can even get situations where the R-squared is large. In other words, the model explains a lot, but none of the individual beta weights on the coefficients are statistically significant. And you can get the beta weight estimates to have opposite signs of what you would expect based on the strength of the correlation, whether the correlation is positive or negative. So there's some really bizarre and undesirable artifacts that happen when we have collinearity in our data when we're trying to come up with good regression coefficients. So what do we do? It's not just in regression, but it can also happen in other predictive algorithms as well. Why does this happen? Well, I think that fundamentally it is a problem of causing. And what the algorithms tend to do is they try to attribute what is causing what, or what is related to what, more correctly stated, what is related to what. And if you've got something that is very highly related, it's trying to parcel out of the two things that are highly related what to attribute this relationship to. Let's look at an example that will sort of help this make sense. All right, so what I've done is I have created a set of data that talks about how much percent body fat is lost for someone who's on a weight loss program. We have their average daily exercise, and we have how well they stick to the diet. And so you can see that these people have lost certain numbers of pounds. You can see how much they exercise in minutes a day, and you can see how well they're sticking to. So here I have plotted the three variables so we can see how they relate to one another. Here we have how well you stick to your diet and how much people lose weight. And you can see the greater proportion of the time they stick to the diet, the greater the weight loss. Here we can see their average daily exercise and their weight loss. And here again, there's a strong positive relationship with their average daily exercise and how much they're losing weight. Finally, we take the two input variables and plot them by each themselves, and you can see that diet adherence and daily exercise seems to be highly related to one another. So essentially, we have three columns of information that have a high relationship with one another. Since strong linear relationships are visually apparent, we should see them in the correlation table as well. Here's a correlation matrix for these variables. So here's the correlation table where we have the outcome variable of weight loss along this column, along this row right here. Average daily exercise is strongly related to weight loss, and the diet adherence is also strongly related to weight loss. And average daily exercise and diet adherence are strongly related to each other. So just based on the scatter plots and the correlation matrix, we can make some reasonable guesses as to what would happen if we try to do a prediction. We could predict weight loss from either of these two variables or from both of them. We prepared three regression models to predict weight loss. The first one includes both exercise and diet adherence. This one includes just exercise, and this includes just diet adherence. I've color-coded them to make it easy for your eyes to follow what's going on. In this first one, both exercise and diet adherence are statistically significantly related to weight loss. And you can see that we have strong R-squareds in terms of weight loss. And this one, where we're only doing exercise, it's also strong, but notice that this coefficient is much bigger than this one here. If I just include diet adherence, this is also much bigger than diet adherence when diet adherence is included with exercise. So what can we learn from this? Well, if you go back to the original data, remember that people were both adhering to the diet and exercising. So there's really two causes for weight loss. If we go and we look at this and only include one of them, we are overstating the effects of daily exercise on weight loss. And here we're overstating the effect of diet adherence to weight loss. It's an attribution problem. If the model can only see one cause, then it attributes all the weight loss to one cause. This example shows that the estimates of the coefficients can change quite a bit when we add or drop predictors that are highly collinear. MLR did a good job of estimating the relative contributions of exercise and diet on weight loss when they're both in the model. However, I would avoid using the only one predictor models because they overstate the contribution of each variable when it's considered by itself. In this case, we do not have the situation where R-squared is high, but the predictors are not significant, so that's not a problem. And the results are in line with what we would expect from the correlations of these variables with the outcome variable. So I think we're okay there. So collinearity has not caused us a big problem in terms of being able to use this model. Also, because R-squared is higher for the multi-contributor model, then we can go with that and have better predictions. In the exercise and diet example, we had two different unrelated things that contributed to weight loss. But we can also have a different situation where sometimes we have multiple measures of the same thing or something that's closely related. Let's look at an example of this. Let's assume that we're trying to determine and predict the weight of a newborn baby by their gestational age, that is the time between conception and birth, and their APGAR score at the time of birth. Well, what is an APGAR score? An APGAR score are 5 tests that they do as soon as a baby is born to see how well the baby is doing, to see how their skin color is, and as a function of how well it looks like it's doing with oxygen consumption, whether the heart rate is up sufficiently, whether or not it responds to stimuli, and also if it has good muscle tone, and if it's crying and really breathing really well. And they add up these scores, and it's a measure of how well the baby does at the time of birth. Well, if we have that, and we also have the gestational age, the time that they have been developing in the womb, can we predict birth weight using these two variables? So if we were to look at a correlation matrix, it might look something like this. Here's our outcome variable. Here's our gestational age. Here's our APGAR score as it relates to our outcome variable, and you can see that the APGAR score and gestational age are related to each other. So we have collinearity, and both of these contribute to the outcome variable. Here's our birth weight that we're trying to predict, and if you think about it, gestational age and APGAR score are really two different ways to assess whether or not the baby is fully developed at the time they're born. If they've been in the womb the full 9 months, the full term, they usually have better APGAR scores. And so APGAR score is another way to measure how well the baby is doing and how well they've developed. So yes, these should be highly related. And so they're not independent. Regression usually assumes that the input variables are independent, and they're not independent here. They're essentially two different measures of the same idea, gestational maturity. In addition to causing problems for multiple linear regression, collinearity can cause problems for other predictive algorithms as well. The algorithms can have a hard time separating out the contributions of highly related predictors. So you want to do a collinearity analysis before you do any predictive data mining. It should just be a standard thing that you do, and you should remove collinearity problems, at least evaluate them, and make sensible decisions about collinearity. Really high collinearity can lead the data mining software not to be able to estimate or complete when it's trying to calculate the algorithms. If you have a plus or minus 0.9 or stronger correlation, sometimes the software won't work, and you can also have more distortion in the beta coefficients for regression. If it's plus or minus 0.75 or stronger, you'll get some. And if you've got 0.65 to 0.74, and again that's positive or negative, you'll get some distortion. But up here, you have more problems. So what can you do? You can use the collinear independent variables anyway. You can drop one or more of them. You can combine them, or there are other things you can do that are beyond the scope of this course, like principal components analysis. So if you decide to use them anyway, like what we did with the weight loss example, you can check to see if there are negative side effects. You can see if the betas are unstable, if they have high R squared but insignificant beta coefficients, and you get these illogical results given the correlations between the variables that you have. If these are not serious, then you should be able to run the models and get the models to be able to be interpreted. But if the side effects are serious, but you're getting good predictions, you can use them for predictions, but you should beware and not use the coefficients in the regression models for interpretation. So let's look at the option of dropping one or more collinear variables. A good rule of thumb is to retain the independent variable that has the strongest correlation with the outcome variable and drop the others. And we do this a lot in this class. So let's look at a couple of examples. In this example, we have a very strong relationship between IV2 and IV3. If we look at the outcome variables, IV3 has a stronger relationship than IV2 does on the outcome variable. So this would be the logical one to retain. If you look at this similar example, except that the effects are negative, and that doesn't really change anything. It doesn't really matter whether this is positive or negative, or this is positive or negative. You're looking for the strongest effect. And so this case also you would drop IV2, and you would keep this even though it has a negative correlation with the outcome variable. Here's the more interesting example where now we have collinearity among three variables. So we have multi-collinearity. IV1 and IV2 are both related to IV3. What can you do? Well, there are a couple of different things you could do. One thing you could do is you could drop IV3 and you could retain these two variables because you have these relationships to the outcome variable. Another thing you could do is you could drop these two and leave this because it has a strong relationship with the outcome variable. What should you do? You should check. You can do either one, but one's probably going to give you a better outcome, and so you could look and see which one is going to give you the best result. Another option would be to combine indicators of the same variable. So if you had two IQ tests and they were on very similar scales like 1 to 10 or 0 to 100 or something like that, then you could average them or add them together, and that would work. If you have measures that are on very different scales, adding or averaging them does not make sense. We can also have problems as it relates to categorical information that is dependent on other categorical information. So basically, in this particular situation, I've hit all the data except for the categorical information that is likely to have dependencies. What do I mean by dependencies? Well, what I mean by dependencies is that if you know the value of one column, a record in one column, you know the value in the other column, or you know that there's a small set. So let's look at some examples and see if we know what we're talking about. So here we have city, and in city we have a finite number of zip codes. So if I know the zip code, I know what city it is. If I know what city it is, I know that there's one or just a few different zip codes for a city. If I know the elementary, I also know what city it's in, and I know what zip code it is in. And Nebo School District is going to be related to a certain number of towns and so forth. And junior highs are going to be related to a certain town as well. So by knowing one value in one column, I know what values are in the other column, or that there's just a small set of columns that are in the other column. So these columns, the information in these columns, are dependent on one another. Well, when you take an algorithm like multiple linear regression, it's assuming that these things are independent. And so it's not the case. There are dependencies between these different columns. It's not very complicated because you can easily figure it out. And as an example, what I did is I made a pivot table and sorted it so that I had city and then zip codes within cities and then junior highs within cities. And you can see that the dependencies can easily be figured out, but you don't want them confusing your algorithm. You really are going to need to decide which things are which, and you're going to have to try to get it so that you figure out which of these categorical columns are going to be the most useful and get rid of the other dependencies. Otherwise, it can cause problems for your algorithms. So let me just give you an example. I broke on purpose by running this data that had all these dependencies through JUMP, and tried to do a multiple linear regression. And the warning that it gave me was that I had an ill-considered problem, and then it sort of like made itself do it, and then it gave me a bunch of messy stuff. And so basically, it shows me that it made an estimate for the cities and then says that they're biased. And then it went down, and further on it went down, and it looked at things it could figure out pretty well and did those. But then there are a bunch of things that it just couldn't do. Non-estimatable, non-estimatable. And so basically it kind of gave me what it could give me, but it figured out that there's some serious problems of dependencies between the data. And so that's a problem. Now, the other thing that we have in here is we also have some cities that are spelled with just different capitalizations, like Alpine in all caps, and American Fork in all caps. And so these are also going to cause problems because that's really the same city, and you need to go in and clean that up. And I give you some instructions of where to go do that and kind of lead you where the tool can help you clean that up, though you don't make an unreasonable number of dummy variables out of things that really are the same.